So today I'm going to talk about recurrent neural networks. So here's a recap about the three lectures that I'm giving here. Yesterday I talked about linear models and structure prediction. So no neural networks yesterday. This morning I'm going to talk about neural language model and their applications, applications of recurrent neural networks to taggers. And in part 3, this afternoon after lunch, I'm going to talk about sequence-to-sequence models and machine translation. Okay, so why, what's the use of recurrent neural networks? So there's a lot of interesting data that is sequential in nature, not just in NLP, but in many other applications. So in NLP, we have, for example, words in sentences. We have in other applications, you have DNA sequences in bioinformatics, stock market returns, time series. And a challenge is how can we represent an arbitrarily long history? And so this is where recurrent networks become useful. So if you remember, and I guess this was covered in the deep learning basics that in the classes that you had in the beginning of the week. So in fit-forward neural networks, we have something like some input x, then there is some affine transformation like this, vx plus c, where v is a matrix and z is a bias vector, and some nonlinearity g, and this gives representations in a hidden layer that I'm denoting here by h. And if this is just a simple network with one hidden layer, then a prediction can be made by y hat equals an affine transformation on h. Okay, so this is very straightforward. How do we go from here to recurrent neural networks? So if it's very simple. Okay, so we assume that there is some temporal index t. Okay, if you think about sentences, this can be the index, the position of the words of the sentence. And instead of having like independent feed-forward layers for every word, what we are going to have is something that depends on the previous state. Okay, so ht now is going to depend on ht minus 1. And so graphically, you can represent feed-forward neural networks like this, where we have the input x mapping to a hidden representation h, and then a prediction y hat. While in recurrent neural networks, there is a loop here, because as t increases, then ht is going to depend on the state in the previous time step. So this is just a pictorial representation. Okay, so what happens if you take this graph and unroll it over the different time steps? If you do that, we obtain something that looks like this. So this is the unrolled version of the graph. Okay, so we are just assuming that there's 4 time steps. There is some initialization of the hidden state that I'm calling h0 here. This can be a parameter of the model. And given h0, I compute h1 by looking at the input x1 and the previous state h0. And from h1, I make a prediction y1 hat. And I keep going this. So I then predict h2 given x2 and h1 and so on and so forth until I have the full sequence of predictions, y1 hats to y4 hats. So in practice, if you want to do a sequence labeling task, for example, there's going to be a ground truth sequence y1 to y4 that we need to compare with our predicted sequence y1 hats to y4 hats, and we are going to incur a cost that accounts for mistakes that we are doing in this prediction compared to the ground truth. Or it could be, for example, just a cross entropy with the probability that we have here compared to the ground truth. Okay, and then we need to aggregate all these costs and compute the loss function for the entire sequence. So I'm going to talk about that in a while. Okay, so this is a description of the recurrent neural network. How can we train the RNN parameters? So if you look at the unrolled graph, it's a well-formed computation graph. It's a DAG. Okay, so we can just apply the usual gradient propagation algorithm that I guess you learned in the beginning of the week. So is this true? Did you learn gradient propagation? Okay, good. And so one thing that makes RNNs different from other models is that the parameters are shared across time. Okay, so every time step, for every time step, the parameters that map from x to h and from the previous age to the current age, they are all shared across different time steps. This makes it possible to deal with sequences of variable size. Okay, and so then the derivatives need to be aggregated across time steps, and the instantiation of the gradient backpropagation algorithm for RNNs is called, by historical reasons, it's called backpropagation through time. Sometimes you see this acronym BPTT for denoting this algorithm. Right, so let's make this a bit more concrete. So let's suppose that we have some weight matrix U, and that the computation of WT plus 1 is going to depend on WT by multiplying this matrix U. So this is now a parameter node in the computation graph. If you want to update the RNN parameters, you need to flow the gradients towards the matrix U. And this is what's going to happen, right? So because this U is shared across different time steps. So in other words, the gradient of the loss with respect to the matrix U, by using the chain rule, can be written as a sum for all the time steps of the derivative of the state ht with respect to U, so the derivative of these parts with respect to U, times the derivative of the loss with respect to h. So this is just a straightforward application of the chain rule. So if you learned about convolutional neural networks, I guess you might have learned about those in the computer vision class. This is basically the same idea when learning the filters for convolutions. So today we're going to look at 3 different usages of RNNs. The first one is for sequence generation, where we're going to use the RNN to generate symbols sequentially by using an autoregressive model. This is particularly useful for language modeling. The second usage is for sequence tagging, where we have a sequence as an input, for example, a sentence with a certain number of words, and we want to return a label for every element of the sequence. For example, the part of speech tag for that word. And finally, we're going to look at the third usage that I'm calling here pooled classification, where we still take a sequence as input. It can be again a sentence, but then instead of predicting one label for every word, we just predict a single label for the entire sentence. For example, it could be a sentiment class for that sentence. And so to do that, we need to pool over the RNN states. Okay, so let's start with sequence generation. And the example that I'm going to consider here is language modeling. Recall what I mentioned yesterday about the different options that you have to define a probability distribution over strings. One of the extreme cases was a full history model, where we defined the probability of the full sequence starting from y1 and stopping in yl. We defined this probability as a product of different probability factors, where each probability is a probability of a symbol yi conditioned on everything that has been outputted in the past. And so one question that I asked yesterday was, are we losing any flexibility by writing the joint probability this way? And I don't know if you still remember the answer to that question, but the answer is that we are not losing anything, because this is just applying the law of probabilities, right? You're just multiplying these individual factors, conditioning on all the past contexts. But on the other hand, despite this huge expressive power, there are too many parameters to estimate. So in particular, if the size of the sentence is unbounded, there are infinite parameters here to estimate. So we don't want to do this. We cannot generalize well with this approach. But one possible idea is, okay, maybe we still exploit the full history, but we compress it in a vector, in a continuous vector. And this is exactly what RNNs do when applied to sequence generation. So yesterday we avoided the full history by considering a limited window, a fixed size window, a kth order Markov model. An alternative to that is to consider all the history but compress it into a vector, and this is what RNNs do. All right, so what are the key ideas of autoregressive models? So the first idea is we feedback the output in the previous time step as the input in the current time step. So if you recall the computation graph that I had here, where xt denotes the inputs, and yt hat denotes the prediction at time t. What we are defining here is, in autoregressive models, we state the input in time step I, this could be t, as the previous symbol that was emitted at step t minus 1. Okay, so we are basically feeding the last symbol that was emitted as the input in the next time step. So the second key idea is to maintain a state vector hi for every time step that is going to be a function of the previous state vector and the current input. And this is the state that is going to compress all the history. And the expression for obtaining hi is going to be basically the RNN equation. So hi is going to depend on xi, the current input, which turns out to be the same as the previous output that we have emitted before by this equation. Plus, it's also going to depend on hi minus 1, which is the state in the previous time step. Okay, so now we have a state at position I. The next thing that we need to do is to compute the probability for the next output. So we need to compute this probability distribution, which we are assuming here that it can depend on the full context. And to define this probability distribution, we just take a simple softmax transformation over an affine transformation of hi. This is it. So it's very simple to take an RNN and define an autoregressive model. So, and now what we're going to do is to look at these steps in more detail. Any question before I do this? Does this all sound familiar? Have you covered this before? Ah, okay. So this is maybe this was covered in the deep learning basics. All right. So I can go a little bit faster then. I don't know. Okay. So let's look at the softmax part. Okay. So this is basically the last part where we have a state vector hi at time step I, and we're going to use this hi to define a probability distribution over the words of the vocabulary. So this is basically a gigantic softmax. So we have a big vector. The dimensionality of this vector is the size of the vocabulary, something like hundreds of thousands. Each entry here corresponds to a word. And we want to assign a probability to every word. Okay, so this entire thing is going to sum to 1. And so what the softmax transformation does is basically, so we first take the state h, we do this affine transformation. So z is now dimensionality size of the vocabulary, and now we just do a softmax transformation on z, which means exponentiating each coordinate of z and normalizing. And this assigns a probability value to every word. And based on these probabilities, we can then sample the next word and keep iterating in this process. So this is what the entire thing looks like. So we start with a special symbol that denotes the beginning of the sequence. This is the start symbol. So from the start symbol, there is going to be some embedding. So this is an embedding layer that computes a representation for each word that is provided as input. From this h1, you compute h1 conditioning on the previous time step h0. This is a parameter of the model because this is a special start state. And h1 also depends on x1. And then we have this mapping from h1 to a softmax And then we're going to sample. So this node here denotes a sampling operation. We're going to sample a word from this softmax distribution. And this is going to output, for example, the word I. Okay. Then for the next time step, I is going to be provided as an input. And we take the embedding of I as x2. From x2 and h1, we compute h2. From h2, we compute this vector, this softmax vector. And then again, we sample, and we get the word like. And we keep doing this until we're generating the stop symbol. So this special thing denotes the stop symbol. As we generate the stop symbol, we are done with generating the sentence. And this is the sentence that we are outputting. And so overall, we define, by following this process, we have a probability value for every string that we can generate. Is this clear? Okay. So this is called the autoregressive model. And so the relevant algorithms that we can think about when generating a sequence using RNNs are sampling a sequence from the probability distribution defined by the RNN. This is what I just showed we can do. The second problem is computing the most probable sequence. And the third one is how to train the RNN parameters. So sampling a sequence is very easy. It's basically the picture that I had in the previous slide. So this is basically the recipe for sampling a full sequence by following the steps in that diagram. What about finding the most probable sequence? So this is a hard problem, okay? If you want to get the sequence that has the maximum probability, according to the probability distribution defined by the RNN, this will require obtaining jointly the sequence y1 to up to the maximum length of the sequence that maximizes the product of all the softmaxes at each time step. And there is a recurrence here. So this h2 depends on h1. It also depends on the previous symbol y1. So this entire thing is going to depend on the full assignment y1 to yl. And so note that picking the best yi greedily at each time step does not guarantee the best sequence. Okay, so if I at the first time step pick the yi that is the most probable, the decisions that I'm going to make afterwards may decrease the probability of the sequence, and maybe the best option was not generating that y1 in the first time step. So despite that, this is what is typically done in applications like machine translation. These are variations of these, like beam search. So with beam search, we can get a little bit better approximations that by doing these greedy decisions, but it's still pretty much greedy. It's just a little bit less greedy. Of course, if you're just doing language modeling, if I'm just generating a sentence, as I was explaining before, this problem doesn't make much sense. Why would we want to pick the sequence with the highest probability? It's just one single sequence. We don't want that. But this is important in conditional language modeling. For example, if you're doing machine translation, then there is a source sentence, and you are conditioning the sentence that you generate on your source sentence because you want it to be a translation of that source sentence. Or if you are doing something like image captioning, our input is an image, and you want to generate a caption for that image conditioned on the image. In that case, it makes a lot of sense to try to look at what's the best possible caption for that image. So we'll talk about these, well, not tomorrow, but in the afternoon, when we discuss sequence-to-sequence models. Okay, finally, we have the last problem of RNNs, which is how to train it. And so the typical procedure for training an RNN is to do maximum likelihood estimation. So in other words, we train the RNN to minimize the cross entropy or the log loss, which I'm guessing is a loss function that you learned already, right? So this means that for a particular sentence, so let's suppose that we have a training set containing sentences that I'm denoting here y1 to l. So this is a sentence of l words. we want to maximize the probability of that sentence according to our model. So we want to pick the theta. Theta denotes the model parameters. We want to pick the model parameters that assign probabilities as big as possible to the ground truth. And this can be written by, since the product of probabilities, the log of the product of probabilities equals the sum of the log probabilities, we can write the probability of an entire sentence as a sum of log of p of each word conditioned on the previous words. Okay? This is basically what makes it possible to decompose our loss function for the entire sentence as a sum of losses for every word that the model is generating. So this is equivalent to minimize perplexity. I don't know if this was already covered, but perplexity is basically an exponentiation of this loss. So it denotes like when the model sees a word at the ground truth word at a particular position, how perplexed is the model by seeing that word? Okay, so you don't want the model to be surprised when it sees a particular word because we want it to assign a high probability to that word in the first place. If we have a good language model, the model should assign a big probability to the words at each position. And so one equivalent way of saying that is we want to minimize the perplexity of the model. Okay, is this intuitive? Any questions so far?
When calculating loss, why does yi depends on its history?
So this is basically okay. So this is the sum of the log of these probabilities equals the log of the product of these probabilities, and the product of these probabilities for every time step I equals the probability of the full sequence, right? This is basically this equation, right? So I'm just taking the log of this, and this becomes the sum of log of these terms. And now the RNN offers a way of modeling this probability distribution at every time step by compressing the context. So it compresses the context in a single vector. Which means that we have a way, by using our softmax distribution, we have a way, once we know the ground truth yi, we have a way of obtaining the probability value of that yi conditioned on the full context, given our current model theta. Does that make sense? Any further questions? All right. Okay, so this is the situation that we have. Okay, so now we assume that there is a ground truth sentence when you are training the RNN. This is the sentence that we have in our training data. I like curry. And then we want to tune the model parameters. So there's a softmax missing here. So then we need to tune our model parameters to assign a probability as big as possible to the sentences that exist in the training set. And this can be modeled by looking at the softmax, looking at the entry corresponding to each of these words, looking at the probability values that softmax assigns to that, and then having a cost function that is just the cross entropy, basically the log probability of each of these ground truth words. And then we need to sum everything, because our loss is going to be defined as a sum. That's that sum over there. So then we need to sum everything, and this becomes our loss function for the full sentence. And we normalize over the size of the sentence. So this is this division by L plus 1. Sometimes you don't normalize. It depends on the task. Okay, so and this is it. This is how we train an RNN. Okay, so hopefully, if you do this, if you have a training set of millions of sentences, and if you keep, if you apply stochastic gradient descent to take the gradient of this loss and optimize the model parameters. Eventually, the model will learn to assign high probability to the sentences of the training set, and hopefully it will generalize well enough such that when it sees a new sentence, it gets a low perplexity value on that new sentence. Okay, so one interesting point about RNNs that makes them different from Markov models, from n-gram models, is that RNNs never forget. Okay, at least in theory, they never forget. So they keep the information for the full context. So they don't have this limited memory window of things that they can condition on. This is a very useful property. This is also the reason why neural language models became the dominating paradigm in the last few years. However, we're going to see that RNNs might still have trouble learning to use their memories. So the model, the RNN that I presented right now, it's not what is used in current models. Okay, this is kind of a pictorial description about what RNNs do, but in practice we use different gatings that are better than RNNs in terms of learning to use their memories. So another thing that is relevant here is this notion of teacher forcing and the exposure bias problem. So these autoregressive models that I just presented, we are always conditioning on the true history. We are not conditioned on the predictions that the model is doing. This is called teacher forcing. So in other words, if you look again at this diagram, this sequence here is the ground truth sequence. This is not the argmax, so the most probable words according to the model. Okay, so we are always conditioning every decision by feeding back the ground truth words that exist in the past context, and this means that the model is never exposed to its own mistakes. So in practice, the conditions at test time are very different. So at test time, the model we are sampling. So let me get to that slide. So this is what happens at test time. At test time, we compute the softmax transformation, and then we sample a word from this softmax, and then we condition what we do next on the words that the model generated. Okay. So if instead of sampling we do argmax, which makes a little bit more sense in conditional language modeling, then we are conditioning on the model's predictions and not on the ground truth. But at training time, this is not what happens. At training time, we are not conditioning on the model's predictions, we are conditioning on the ground truth. So there is a little bit of a mismatch between training and test conditions. And this strategy of conditioning on the ground truth is called teacher forcing. And the problem that this mismatch between training and test is called exposure bias. It means that the model is never exposed to its own predictions. So at test time, if it does a mistake early on, then it was never trying to recover from that mistake. So it can keep doing worse and worse decisions as it goes. And there's a few ways of trying to avoid this problem. I'm not going to talk about them now. One way is to use reinforcement learning, for example, where we only get a reward after a full predicted sequence, and then the model is trained to optimize that reward. But this complicates training a little bit. Yeah, so this is the current area of research. Any questions about this?
So, so this problem of teacher forcing, basically, is it what is the sort of the fundamental problem? Like, is it because we cannot condition on the model prediction during the training, or so one way of solving this is to basically also incorporate the prediction of the model as the conditioning part as well, right? So I don't know whether this would be maybe one of the solutions.
Yeah, so this is basically what current, as I was saying here, there is a current area of research to avoid teacher forcing. There are methods that try to avoid that by kind of having a switch where sometimes they use the condition on the previous decision that the model did. Other times they use the ground truth. This is called scheduled sampling. There's a few papers that do that. There's also reinforcement learning techniques that you can use when you just let the model predict the full sequence at training time, and then we have a reward that compares the sequence that got generated with the ground truth sequence, and you want the model to optimize that reward. The reason why this is not the mainstream, well, at least if you think about applications like machine translation, as I'm going to describe in the afternoon, this is not the mainstream. This is not the way that most models are trained, because it slows down training a lot, and also schedule sampling has other problems. Yeah, so I'm not going to talk about them today, but I would say that the problem is still not solved. So the best that we have so far, it's basically still teacher forcing, even though it's not super satisfying. All right. Okay, so we can also have an RNN over characters instead of words, right? Why not? So we have this is a sequential model. We can just condition on characters. Well, maybe this makes a lot of sense for Thai, because there's no clear word segmentations in Thai. And maybe, I don't know, does anyone have experience using RNNs or LSTMs for Thai? Yeah? Do you segment over characters or something else?
We do word segmentation beforehand.
Okay. Yeah, so there's a bit of a trade-off, right? So if you segment over characters, then the model can generate words that were never observed at training time. For language that have a rich morphology, it can be beneficial. But on the other hand, it also needs to memorize more information to make the right predictions. So sometimes it's much easier just to guess the full word at once, instead of doing all these time steps to generate character after character until the full word is produced. Computationally, RNNs over characters are also more expensive because they require more time steps. But yeah, so sometimes it's useful to consider character level language models that can generate any combination of characters, and taking into account these advantages. But here's a few examples taken from André Karpati's blog about how far we can go with a simple character level RNN in this case, trained on Shakespeare's books. It generates text that's kind of at first sight looks like Shakespeare. Right? It's better than what we would think of. Compared to n-gram models, usually you can get much better quality by using RNNs if you have enough data to train them. Here's another example, a math paper. So this doesn't make any sense, of course, but the symbols can be convincing at first sight. It's interesting that the numbering of the lemmas is correct. Like you have 0.1, then 0.2, then 0.3. Well, this is because it's not outputting the numbers themselves. So there's more examples like C++ code. This looks like C++ code, right? Yeah. So these examples are already quite old. So they are from 3 years ago, I think now 4 years ago. So now we have even more impressive language generators, things like GP2 and so on. So I'm going to talk briefly about that in the last lecture in the afternoon, when I talk about transformers. Okay, so we covered the first usage of RNN, sequence generation. Let's move to the second one, sequence tagging. So in sequence tagging, just to recap, we are given an input sequence x1 to xl. This can be, for example, words in a sentence. And the goal is to assign a tag, for example, a part-of-speech tag, to each element of the sequence. And this is going to yield an output sequence y1 to yl. So the size of the output sequence is now the same as the size of the input sequence. So this arises in part-of-speech tagging, named entity recognition, and so on and so forth. So the key difference is with respect to sequence generation, which was a task that we considered before, is that now the input and output are distinct. So you don't need this autoregressive model anymore. We can still have autoregression with respect to the labels, but it's not really necessary. And the length of the output is known. Okay, so you want to output exactly one tag for every word for that particular position. Is there a question? Yeah. Okay, so kind of a concrete example, the same sentence that we have yesterday, sentence and the proto-speech tags for every word. Okay, so how can we solve this? So we are going to take each word of the inputs, and they're going to generate inputs x1 to xl. They are word embeddings. Did you cover word embeddings already? No? Okay, so I should have a few slides on that. So by word embeddings, I mean continuous representation of a word. So there are many methods that are able to learn vector representations of words, things like word2vec. I don't know if this is familiar to you. But for every word in the vocabulary, let's suppose that you have a vocabulary with hundreds of thousands of words, we represent each word as a vector in a lower dimensional space. For example, a space of size 100 or 300. What methods that learn these word representations capture is that words that are semantically related, they get mapped to the same area, the same region in space. So, for example, we have people's names all clustered close to each other, then weekdays in another group, city names elsewhere, and so on. And this makes it particularly appealing for tasks where we want to model some semantic proximity, some semantic similarity between the words that you generate, which is something that we cannot do if you use something like a N-gram Markov model, where we are basically working with one hot representations of words, but there's no way of modeling how similar the words are. So this is also part of the success of this neural language model, the ability of dealing with word embeddings. Okay, so all right. So how can we build an RNN-based part-of-speech tagger? So as before, we are going to maintain a state vector, hi, for every word at every position. And this state vector hi is going to be a function of the previous state vector and the current input. So same equation that we had before. And so this state is going to compress all the input history. So it's going to kind of remember everything that was just before that word in the sentence. And then we have a softmax output layer. The dimension of this softmax is going to be the number of possible part-of-speech tags. So it's much smaller than the vocabulary size. Typically, something between 10 and 20, depending on the conventions of the tree-bank annotators. So this softmax output layer is going to compute the probability of the current part-of-speech tag given the current and the previous words. So we have this softmax expression over here. So this is pretty much, mathematically, it's pretty much similar to what we had before, except that you don't have this autoregressiveness. And now there is a separate input and output. So there are ways of improving this model. So one thing that you might be wondering is, why do you just condition on the words on the left and not on the words on the right? So if you want to do that, we can use something called the bidirectional RNN, where we have two RNNs, one running left to right, another one running right to left. So one is capturing the left context, and the other one is capturing the right context of every word. And then we can combine, you can concatenate the states of these two RNNs and use this concatenated vector to produce a prediction for the part-of-speech tag at that position. This is what is traditionally done in these sort of models. And we can also have a nested character level RNN or CNN. This has been done in several works to obtain embeddings for unseen words. So this is particularly relevant if you get a word that is not in our vocabulary, which in practice is always going to happen. So at test time, we're always going to find words that you never saw at training time. And so if you have a character level model, maybe nested with the word level model, we can still learn a representation, we can still learn an embedding for that word, even though you never saw that word at running time. And so this, the model that with these two improvements achieved state-of-the-art performance on the Prentry bank and several other benchmarks. So there's a lot of work done by a few people using this approach. So in practice, they didn't use RNNs, but they use LSTMs. But I'm going to cover that in a while. Okay, so this is what bidirectional RNNs look like. So in this case, this is an example for a character level model for a single words. So we have one RNN running left to right, another RNN running right to left. We just concatenate these two. And in this case, we pull them together. And this is the embedding that we are learning for these words that we might never have seen at training time. Okay, so other examples, named entity recognition. So this is also an example that we saw yesterday. Here we want to identify word segments that refer to entities, and you want to classify those entities as persons, organization, location, and so on. And we can use this BIO tagging scheme to perform that. So the model that we just described for part-of-speech tagging, it works just as well for NER. The only difference is that NER has constraints about tag transitions. So, for example, you cannot have a inside person after begin location. And so one way of addressing these constraints is by adding a CRF output layer similar to the technique that I was describing yesterday. Right. So this is where we can basically use this dynamic programming that I taught yesterday that is able to take into account constraints between these transitions of tags. So the full recipe is like this. We just use the RNN to compute scores for the emissions instead of using these features and weights that I had yesterday. For the transitions, we can either compute scores from the same recurrent layer, or we can just have an indicator feature that looks at the combination of the two tags and learn a parameter for these two tags and put the two things together. And then you just need to replace the softmax output layer by a CRF output layer that looks at these emissions and transition potentials. So at training time, we just need to plug the forward-backward algorithm in the gradient backpropagation. So I think I rushed yesterday a little bit, but it's possible to compute the gradient in a CRF model just by computing the posterior marginals. And this is something that we can do by using forward-backwards. And this makes it possible to train a neural network end-to-end with gradient backpropagation that has a CRF output layer by just using dynamic programming in the last step. And so this is at training time. At test time, what we do is just to compute the scores using the RNNs, and then using Viterbi, the Viterbi algorithm, to predict the most likely sequence of tags. And so a variant of this model, using a BILSTM instead of an RNN, achieved the state-of-the-art in various NER benchmarks. I think this is no longer true, but it used to be true at least before BERT. Any questions? Okay. So we covered the first two cases. Let's look at the last one, pooled classification. So here we are given, again, a sequence as an input, but now we have a single output. So we want to have a label for the full sequence. All right, so we can still use the RNN to capture the input sequential structure. Now, the new thing that we need to do is to pool the RNN states. So we need to map them to a single vector. Instead of having a vector for every word, we want a vector for the full sentence. And then we want to add a single softmax to output the final label. So this is pretty straightforward. There are several pooling strategies that you can use for this. So the simplest possible is just to pick the last RNN state. If you have a unidirectional RNN, you can just take the last state as our sentence representation, and then make our decision for the label for that sentence based on that single vector. So, you know, this state that we get at the last RNN position results from traversing the full sentence, which means that when we compute it, it has seen everything in the sentence. However, there's some recency bias on this state. So it's going to remember more the less things that it saw in the sentence, and it's going to forget a little bit about the initial things. So this will become more clear when I talk about some of the disadvantages of RNNs and problems that they have to deal with memories. So this is basically the point that I'm making here. So memory about the earliest words will vanish a little bit. So other alternatives to this are using a bidirectional RNN, so one that goes left to right, another that goes right to left, and then combine both less states of these two RNNs. So if you do that, then we have a system that remembers more the less things, and another state that remembers more the initial words of the sentence. And when we concatenate the two, hopefully we still have enough information about the full sentence. Another option is to do average pooling, where we just average all the states that we compute at every time step in the RNN. So the best approach depends on the problem. So here's an example for a simple classification problem. In this case, sentiment analysis. So we have this input sentence. I don't hate it. It's a tricky sentence because hate is generally negative. Don't hate, it's not positive, but it's probably neutral. And we want to output a single label. And in this case, I'm illustrating a unidirectional RNN and the simplest pooling strategy where we just take the last state of the RNN. So this is the last state of the RNN, and this is what is going to be used as a sentence representation to make our prediction. But so in general, recurrent neural networks are extremely versatile. And this is also what made them extremely popular. So there's a nice blog post, again by André called The Unreasonable Effectiveness of RNNs. It's already 4 years old. It might be a bit outdated, but some of these things are true. So you can use RNNs to compute, like for example, one-to-many. Like here we have as input, like we have one input and we want to output several things. I didn't cover that. We can also do that for many-to-one. This is basically the sentiment classification example that I had before. We can do that for many-to-many. This is, for example, machine translation. I'm going to cover that in the afternoon, where we have a sequence as inputs, and you want to output a sequence that might be of different size as the outputs. And we can also do it, again, many-to-many, but assuming that each element in the output is going to correspond to each element in the input. So this is basically the part-of-speech tagging example. Okay, so now I'm going to talk about the vanishing gradient problem, assuming that this was not covered yet. Was it? Sort of? Okay. So I'll go a little bit slower here than maybe the speed that you got in the other class. So as I was saying before, training the RNN is done by backpropagation through time. Let's look a little bit more into what happens to the gradients as we go back in time. So this is again our RNN. So we have inputs x1 to x4, and we compute each state ht by looking at the previous state and the current input by using those equations on top. And then, well, for this particular case, I'm just assuming like a pooled scheme where we just take the last state, and the last state is going to make a single decision for the full sequence. So at the end, we get a prediction y hat, and we incur some loss with respect to a ground truth y. Okay, so let's look at what the gradients are going to look like. So if you want to compute the gradient of these laws, I'm calling it f now. So if you want to compute the gradient of these laws with respect to the model parameters, so the model parameters are basically this matrix V, this matrix U, this bias vector C, W and B. So if you look at the gradients, so recall that U is shared across all the time steps. So this for this model, W and B are not a problem because they only appear once here. But let's focus on the U part and the V part as well. But the U is the most problematic one. So this is basically the matrix that is being shared across all time steps that is going to express the dynamics of the system that makes HT depend on HT minus 1. So in order to compute the gradient with respect to U, we need to compute the gradient of the loss with respect to each of the states HT. Okay? And in particular, the gradient of the loss with respect to H1, which is the first state, it's going to be, by calling the chain rule, it's going to be the product of many gradients. The gradient with respect to the gradient of H2 with respect to H1 times H3 with respect to H2. So each of these things is going to be a matrix. So these are Jacobians. They all multiply together, and then in the end we have the gradient of our prediction y hat with respect to H4. And here we have the gradient of the loss with respect to y hat. So I said prediction, but you can imagine this is just a softmax. Or it's just the state before the softmax, if you want. But so the point is that you need to multiply all of these things, and as our sequence gets longer, we get more and more terms in this product. And how do these gradients look like? So the gradient of HT with respect to the previous HT minus 1 can be decoupled as the gradient of HT with respect to ZT. This is basically before applying the nonlinearity. So I'm calling ZT to the thing that is before the nonlinearity. So this can be written as the gradient of HT with respect to ZT times the gradient of ZT with respect to the output of the previous hidden state in the previous time step, HT minus 1. Okay, so and so by looking at the expression that we have for writing HT as a function of ZT, the first one is just a diagonal matrix because we apply this nonlinearity independently over the different units. The second one, the gradient of ZT with respect to HT minus 1, if you look at the expression, it's going to be, so ZT is basically this part inside, so the gradient with respect to HT minus 1 is going to be this matrix U. Okay? So this is going to look like a diagonal matrix times U. And then there's three cases that can happen. So recall that this is all inside this product, okay? So we are multiplying by this matrix over and over. So there are three cases that can happen. So the first case is the largest eigenvalue of U being exactly 1. If that happens, then gradient propagation is going to be stable. So you know the magnitude of the gradient is not going to increase or decrease. It's going to stay constant. The second case is the largest eigenvalue of U being smaller than 1. If that happens, then the gradient is vanishing as we keep taking these products one after the other. So there's going to be exponential decay. The gradient is decreasing exponentially fast. The third case is the largest eigenvalue of U being bigger than 1, in which case the gradient is exploding. So the gradient is getting bigger and bigger as we keep taking these products. So exploding gradients, they can be dealt with by doing techniques like gradient clipping. This is a little bit of a hack, but it sort of solves the problem with exploding gradients. So we don't need to concern so much about the case where the eigenvalue is bigger than 1. So gradient clipping is just truncating the gradient if it exceeds some magnitude. I think I have a slide that explains that later. Vanishing gradients are more difficult to solve. They're also more frequent. So in practice, this means that long-range dependencies are going to be difficult to learn. So in short, this means that RNNs are good because they can condition on the full history, but in practice, they have problems remembering everything that is far away in the history. So what are the solutions for this? Here are some possibilities. We can have better optimizers. I'm not sure this will solve the problem. We can have some sort of normalization to keep the gradient norm stable across time. We could have a clever initialization that guarantees that we are always close to unit eigenvalues. So, for example, specifying, initializing U as a random orthonormal matrix. So this is a matrix where the largest eigenvalue is going to be 1. Or we can look at alternative parameterizations. This is the more mainstream solution by using something like LSTMs and GRUs. Okay, so let's look at gradient clipping. This is the solution for exploding gradients. Gradient clipping is just, you compute our gradient as usual. Then we take the norm of the gradient. If the norm of the gradient exceeds a threshold C, then you just renormalize the gradient. You just scale it such that the norm is going to be exactly C. So this way we guarantee that the gradient is never too big. Another technique is to do it element-wise. So we can just look at each coordinate of the gradient. If that coordinate exceeds C, you just replace it by C and keep the sign. So this is used in most deep learning packages hidden somewhere. Okay, so there's a constant somewhere that you might be able to customize. But if you use a implementation of RNNs in TensorFlow or PyTorch, this is actually being done under the hoods. Okay, so I'm going to describe two alternative parameterizations of RNNs. The first one, GRUs, gated recurrent units, proposed by Kyung-Yum Cho and others in 2014. And the second one, long short-term memories that precede GRUs in time, but are a little bit more complicated. In practice, they might perform a little bit better. So the intuition about these alternative RNNs is that to avoid multiplying these gradients across time, which is the source of the problem because it leads to this exponential growth or exponential decrease, if you think about vanishing gradients, we want the error to be approximately constant. And so these alternative parameterizations, they solve the vanishing gradient problem, but they still have exploding gradients. So we still need to do gradient clipping. So here's what GRUs try to do. Here's the intuition behind it. So the problem is that the error must backpropagate through all the intermediate nodes. So if you have a long sequence, you need to backpropagate the gradient all the way through. Okay, so one idea is if we could create some sort of shortcut connections, if you can disconnect some of the units here, maybe in a component-wise manner, then we could propagate information faster from one point of the sequence to a point that is very far away. And so one way of creating these shortcuts is to do it adaptively by creating some special gates. So this is what GRUs do. They start, so in a standard RNN, the expression for updating the next time step looks like this, looks like the first line without this. So what they do is they introduce two gates, a reset gate and an update gate. And both these gates are computed as sigmoids over that depend both on the current inputs and the previous hidden state in the previous position. And so the reset gate is basically being used this way. So it's going to pointwise multiply every component of the previous state ht minus 1. And if the reset gate is 1, if one entry of this vector rt is 1, then this is basically doing the usual thing. But if it's 0, it's going to disconnect information coming from the previous time step. So it's basically allowing to ignore information from the previous time step, and it's going to just look at the current input. The update gate does, so it's also a function of the previous time step and the current input, and it's applied this way. So by doing this first update, you compute like a candidate update. Let's call it ht tilde, which is not the final state, but it's just like a candidate for that state. And then the update gate is going to be an interpolation between ht tilde and the previous state. So if the update gate is close to 1, then this is basically using the candidate update. if the update gate is close to 0, it's going to ignore the candidate update, and it's going to instead copy the state in the previous time step. So this is what creates a shortcut, because it's just propagating the previous vector as it is, and this is done in a coordinate-wise fashion. So some coordinates of the state may be shortcutted, others may be updated as usual. Is intuition clear? Yeah, so if RT is all ones and UT is all ones, then you get a vanilla RNN. Okay, so the second possibility, yes.
How does that help with gradient vanishing?
So this is basically creating these shortcuts kind of reduces the long-range dependencies between two positions that are very far away. So I'm not computing the gradients explicitly here, but intuition behind this is that if sometimes you reset gates and sometimes the update gates are just copying the previous states, then we avoid multiplying too many times the matrix U, and this is going to kind of mitigate that problem a little bit. So yeah, it's more like an intuitive explanation. But if you do the math and compute the gradients, you might get like a very long expression. But you might see that if the values of the reset and update are often creating these shortcuts, then you're going to have fewer products by this matrix U, which is the cause of the problem. Any further questions? Good point. Yes, so the original question was, how does this solve the gradient vanishing problem? And my explanation was that kind of this exploiting the shortcuts, you get fewer of these products, which mitigates the problem a little bit. Okay, so let's move to LSTMs. This has been proposed in 1997. And so the key idea of LSTMs is to use memory cells. So we are going to call them CT. In addition to HT, that are the states, the recurrent states, we now also have these memory cells. And the intuition behind it is that, again, the problem is this multiplicative effect in the updates of RNNs. What LSTMs try to do is to flow information additively through these cells, so through the cell CT. And this is done, the flow is controlled by using these special input, forget, and output gates. So this is basically what they are doing. So there is a sequence of cell states, and the H's, the states coming from the LSTM, are the output of this sequence of memory cells. And I'm going to explain the dynamics of the memory cells in a minute. Okay, so this is what LSTMs do. We have these three gates: a forget gate, an input gate, and an output gate. So we start by updating the memory cell CT by looking. So let's forget about the red gates for now. If this is all ones and this is all ones, so the way we update CT is basically by adding CT minus 1 to this nonlinearity transformation with respect to the previous HT minus 1. And note that this is now additive, it's not multiplicative. So it's going to make the gradient with respect to CT a little bit easier, a little bit better, because you don't have these products of matrices. And now these gates are controlling how much of the information we want to keep and how much we want to forget. So they are all a function, again, of the current time step, the current inputs, and the previous time step. And the forget gate is basically, if the forget gate is all ones, then this is retaining everything that exists in the previous memory cell. So this means that we are kind of just retaining everything that existed in the previous time step. If the forget gate is all zeros, this is resetting the memory cells. So it's ignoring everything that is in the past. The input gate is doing the same thing for the other term. So if the input gate is all ones, this is going to compute the function of the previous LSTM state. If the input state is all zeros, it's going to ignore this part. And if the forget gate is 1 and the input gate is 0, this is just copying the previous memory cell. And finally, the output gate is again a function of the previous, of the current inputs and the previous time step, and it's used to produce the final update for the LSTM state. So the HT is going to be the pointwise multiplication of this output gate and a nonlinearity applied on the memory cell. So the dynamics here are a bit more complicated than your GRUs. This is what these memories look like. You know, all these things are representing the different gates. But you know, it can basically address the same problem by using these additive dynamics instead of multiplicative ones, thanks to the memory cells. So this might sound a bit obscure if you never saw this before. So I recommend you to look again at the slides a bit later and follow some of these pointers. There's a very nice blog post that explains this in more detail. I found them very useful to understand what LSTMs are doing in practice. Okay, so then we also have bidirectional LSTMs. It's the same story as in RNNs. It's the same thing as a bidirectional RNN, but instead of using a left-to-right RNN and a right-to-left RNN, it uses a left-to-right LSTM and a right-to-left LSTM. And this is usually called a bi-LSTM. And so there's several success stories with bi-LSTMs in many different applications, including time series predictions, speech recognition, name identity recognition, machine translation. I'm going to talk about that in the afternoon. You know, several deep contextual word representations like Elmo and many others. And in practice, it's you know, compared to more recent architectures like transformers and so on, they are much easier to train. They are much less sensitive to hyperparameters. So it's fairly easy to start with a model that is not too complex, with just 1 or 2 bi-LSTM layers, and to apply to a particular sequence tagging problem and get some decent performance without losing a lot of time doing hyperparameter tuning. With transformers, I would say this is a little bit more complicated. Okay, so here's a summary. Oh, I don't know where I'm with time. 15? Okay. Okay, so here's a summary so far. So better gradient propagation is possible if you use additive instead of multiplicative recurrent dynamics. This is the motivation for LSTMs. Recurrent architectures are still an active area of research, but in practice it's very hard to beat LSTMs. There are other variants of LSTMs that simplify some of the gates. There's also extensions for non-sequential structured inputs and outputs, including things like recursive neural networks instead of recurrent recursive. This is basically extending the idea of RNNs to things that are not sequences, but for example, trees. There's also applications of RNNs to image classification, to computer vision, for example, models like pixel RNN. Okay, so I have 15 minutes, right? So I can either cover a few examples that go beyond sequences, that are some of them less related to NLP, or I can get ahead and start covering the slides in the afternoon, because they're a bit longer than the presentation that I had this morning. Which of these two do you prefer? So who would rather cover this part now? Okay. And who wants to jump to machine translation? Okay, I think there's slightly more people in the first group, so let me go this way. All right, so far we've talked about recurrent neural networks. They are designed to capture sequential structure, but if you have, for example, a tree as an input and not a sequence, can we still use the same intuition? The answer is yes. It's also possible to tackle these structures by using recursive computation by something called recursive neural networks. So this was proposed by Richard Zucker and others for parsing images and for parsing texts. In the simplest formulation, they assume a binary tree, which means that each node except the leaves has exactly 2 children. And the way the scores are propagated are basically bottom up in the tree. So these C1 and C2 are the vectors that represent the children in the tree, and we use C1 and C2 to update the state for the parent P. And so if you do this bottom up, then we end up with a vector for the root of the tree. So if you want to classify a tree structure, then we can we can classify also each node in the tree by using this technique. So if you append a softmax output layer to each node in the tree, you can have a label for every node. Here's an example. So this is particularly useful in some text applications because it's good for capturing compositionality. So if you have a sentence like this, so this is a sentence in English. A crowd enters the historic church. Then this is all part of a noun phrase, and if we figure out the right tree structure, then we can compute a representation for this noun phrase by taking these 2 children, historic church, and now this vector is representing not just church, not just historic, but the combination of these 2. And the same thing goes for the other constituents. And at the end of the day, we get a representation for the full sentence that hopefully captures everything that the sentence is saying. But by taking into account this compositionality as opposed to going left to right. The same thing also works for images. So if you take patches in the image, if you identify some objects in the image, and we try to describe a scene by parsing, by describing the relations between these patches, then we will get something like this, and you could get a vector representation for the full image that kind of describes the scene, taking these relationships into account. So I don't know, are there people here working in computer vision? Okay, so this is not my area, so correct me if I'm saying anything that doesn't make sense. But so this used to be like a hot topic a few years ago, parsing natural scene images. Okay, so of course, the same way we had LSTMs to extend RNNs, we can also do the same thing for recursive neural networks. So you can have something called 3 LSTMs that are basically the LSTM analog to this. And so this has been used, for example, for fine-grained sentiment analysis. So here the task is the following. Instead of computing just a single score for the full sequence, the sentiment score, we are going to compute the score for every node in the parse tree. So we first parse the sentence. This is a binary tree. And then each node, which is going to represent a constituent, gets a sentiment score. So for example, if you have here slow and repetitive, this is the node that spans these 2. I don't know if you can see the lines there, but this is basically a span of this node. So slow and repetitive is going to have a sentence representation, is going to have a vector representation. And so this part is a little bit more positive, but the combination of the 2 is going to compute something that takes into account all this compositionality between words. Okay, so the other example are applications in images using something called pixel RNN. We covered the case where RNNs were applied sequentially to 1D sequences, but images are different because they have 2 dimensions. So what can we do about that? So pixel RNNs are 2D extensions of recurrent neural networks. They can also be used as autoregressive models to generate images by generating pixels in a particular order that we need to specify, conditioning each pixel on pixels that have been already generated. And there are several variants of that. So here are some examples. So for example, we can generate this pixel conditioned on kind of this structure that considers the neighboring pixels. There's also variants that use convolutions instead of recurrent neural networks. Or we can, so another option is to condition the pixel on the previous state, the state of the pixel on the left, and the state of the pixel on top. So this is still possible. And this generates images that look like this. Probably not the most impressive these days. I think people were very happy about the quality of these images 3 years ago, but now there's better techniques. But so even more generally, you can also use the variants for graph LSTMs, or instead of having a tree as an input, we have a graph. So this subsumes both the tree LSTM that I was describing before and this 2D RNN that I was describing now, the pixel RNN. So if you have a complex structure like a graph, we can generate a state for each node in the graph by conditioning on the adjacent nodes. If we define an ordering by which we generate these labels. So this is it. To conclude, recurrent neural networks allow to take advantage of sequential input structure. They can be used to generate, to tag, to classify sequences, and they are trained with backpropagation through time. The vanilla form of RNNs have some problems. So they suffer from vanishing and exploding gradients. And LSTMs and other gated units are ways of mitigating that problem. So when we usually talk about RNNs these days, we typically mean LSTMs or something similar. They can be extended to other structures like trees, images, and graphs. So this is it for today. I don't know, am I too ahead in time or not? Yeah? So should I start covering the afternoon part? Do you guys feel tired, or what time is it? 10:05. Sorry? Okay, so any questions? There is one question over there.
What are the benefits of the trees LSTMs over the normal LSTMs?
For text?
Yeah.
So the big benefit is taking into account compositionality. So if you want to model the structure in text, language is very compositional, right? So you can have like long-range dependencies that are created by syntactic relationships between, for example, a noun and a verb. So you can nest substructures in sentences. And if you force the model to propagate everything in a left-to-right manner, even with LSTMs that are better at remember full contexts, they might still kind of lose track about where is this verb, which noun is this verb referring to, right? And if you parse the sentence using constituent parsing or dependency parsing, and then we have an LSTM condition on that syntactic structure, then it has like a easier access to the nouns that are modifiers of that verb, for example. So in practice, I never saw one application where we gain like many points by using trill STMs instead of sequential RNNs, sequential STMs. But this is the main motivation for using them.
I see. So basically, trees, the structure like trees is gonna see more like in practical.
It's going to if you have a good intuition about where that tree comes from. For example, if it comes from a parse tree, and if the sentence is long and complex, then you might have like a better way of establishing dependency between states than if you have a left to right sequence model.
All right, thank you.
Can you back to slide number 50? My question is why just largest eigenvalue of U exactly one gradient propagation is stable? Why?
So why the gradient propagation is stable when the largest eigenvalue is 1? So we are multiplying together these expressions. This is a diagonal matrix. This is a matrix that is not diagonal. If we multiply several matrices, or if you take the power of a matrix, which is basically what happens if you take all these products, things are going either to vanish or to explode unless the largest eigenvalue is 1. So that's just a mathematical explanation.
Why don't we care for the minimum eigenvalue also?
I think the largest eigenvalue is the thing that matters here. But that's a good question. I'll need to think more about this. I don't know if the minimal eigenvalue matters. Do you have any intuition about why the minimal eigenvalue is also important here?
I don't have one. I just think that to claim that the largest one, only the one that matters, needs justification, I think.
True. Yeah, I think that there is some theory that explains, that tries to bound the spectral norm of matrices based on the largest eigenvalue. So this is related probably with spectral norm. So I don't have the exact explanation here right now, but I think the relevant thing is the maximum eigenvalue that is related to the spectral norm, and not the minimum. I think the minimum eigenvalue is not going to be very relevant here. So I'm hand-waving here a little bit, but this is kind of what is understood right now about the dynamics of RNNs.
So I also have one question related to it. So for feed-forward neural network, so this they also have the problem of gradient vanishing as well, right? So it's happened for the same reason, right? If we have a very deep neural network, really.
Yes.
So it's the same reason.
It's related. I'm not sure if it's exactly the same, because if you have a very deep neural network, typically you don't share the parameters for every layer. And this is specific for RNNs, right? So in RNNs, you are sharing the parameters for the different time steps. So in deeper RNNs, instead of having all the same U being multiplied over and over, you have different matrices being multiplied over and over, right? But yeah, so I'm not sure if you can argue about the eigenvalues of those matrices or not, but you still have vanishing gradient problems. That's true.
So the different then in feed-forward neural network, you have different U.
Yes.
In that case. Okay.
Yeah. Okay. Any further questions? If there are no more questions, I will. Oh, okay, there's still one more.
For the sequence model, the order is matter, right? The orders of the sequence is matter. Do we have any other options that compromise on order, like for the word restaurant, we can write it as a rentrées, and it also means the restaurant as well. Do we have the model or the approach that compromise on orders of the sequence?
So the RNNs are sensitive to the order of the sequence, right? Because the way the states are updated depends on seeing each symbol in a left to right transversal. I don't know if this was the question that you were asking.
Some sequence not have the strict order. It can be loosely.
So you want the opposite. You want to have a representation that is not that does not depend on the order.
Maybe like that. Not depend on orders. It's yeah. Different orders can be mean to same thing.
Okay. So that we don't get with an RNN directly. There are models that can give you that. Like for example, transformers are able to do that. There is a way of so transformers are insensitive to the order, and they usually model the order by having a positional embedding. That well, I will cover that in the afternoon. But yeah, so I will not use an RNN for that. Even though sometimes people use RNNs for sequences, even when the order doesn't matter, if they have a set, for example. But then, they don't get like representations that are invariant on the order by which we process each element of the set.
Thank you.
Okay, if you have any questions, you should ask offline and take a break. Okay.
All right.
So yeah, so I think that would be the end of the second session for NLP. And now it's time for the break. So let's take a break for 30 minutes. And if you have any question about the lecture, just ask Andrea offline. Okay. So see you again in 30 minutes. So let's start at